I think there's a long
All right, well, let me get you guys started so we can call it, I guess, closure to this chapter, and maybe with a little luck get started with the next chapter where we take what we've just learned here, Faraday's law, and apply it. So, well, more on that if we get that far. But I want to do a bunch of examples for you today, starting with the chance to throw some homework back at you. Here is this big box that is sitting in the lab. These are all the papers that have gone around at least one time and for whatever reason were not picked up, including a handful of tests that weren't collected last lecture. And slowly getting your stuff graded and recorded. And I got a few graded, at least enough to stay even this week. So maybe this weekend I can do some more catching up. But if you've been following along in the grade sheet online, you will see that the spreadsheet is filling up significantly. And now you've got 2 exams and a bunch of homeworks and labs. So probably about 40% of your grade is right now sitting there on that spreadsheet. The other 60% still to come. Most of that being the 3rd exam that comes out on the last day of class, and then the final exam, which comes out on the Tuesday of finals week. So, or at least you take it then. It'll take me a while to grade it. But let's look at this chapter 31 as we put kind of closure to it. Both the good and the bad, as I was trying to say last time, is simply this. That, right here, this is the whole chapter. And I might as well joke with you again. You want to know the answers to all the homework problems here for chapter 31, and for that matter, 32. Right there. Guarantee it. It is, the EMF is produced by a changing magnetic flux. And so any way we can change the flux, and that's the hard part. There's a lot of ways of changing the flux and a lot of scenarios of changing the flux. But any way you can change the flux, that will produce a voltage, an EMF. And if you put a wire there with some resistors, you would get current. And if you got current, you would get magnetic fields. And so this can get real complicated really quick. But the main thing to remember is simply this, that an EMF is produced by the change in flux. End of story. Now, the negative sign is helpful. We call the negative sign thank you. We call the negative sign Lenz's law because that will help us with the direction. And so it helps me personally to do this, to say, I am just going to worry about the EMF. End of story. And I will not worry then about the sign out in front, plus or minus. I will use my right-hand rules that I've been learning, realizing that the voltage or the EMF that is produced in such a way that it opposes the change in flux. That's what the negative says here. So let's go back to the example we were discussing here. It's this picture here. What if we had, oh wait a minute, this is a little different. Didn't we have one go in the other direction? Bummer. Let me be a little more consistent. I know your author gives you a picture of both of them, one going out and one going in. This is the one going out. All right, so when we left last time, we were looking at this one, and the question would be something along these lines. If you have, in this case, a metal bar laying across 2 rails, the 2 rails are then connected to a resistor. If you were to pull that metal bar, and in this case they're pulling it with a velocity v, Would anything... And I'm hoping you will see that, yes, we will get an EMF if there's any change in flux. And I hope you see that as this metal bar is moving out, the flux going into this rectangle that is created here would get larger and larger and larger. And so your author has shown with green X's, which is the magnetic field going in. And so as this bar moves out, more and more flux is going into that little rectangle. Okay, so there is a change in flux. And if there is a change in flux, then there's an EMF. If there's an EMF and a closed loop, there would be current. And if there's current, there would be a magnetic field and a magnetic flux created from that current. Let's call that a secondary effect. And so the primary field is this green dots, or these green X's, as it pulls along. That primary field, as we pull it, this bar across, produces an EMF, which produces a current. That current produces a secondary field. And the key to figuring out the direction of the current is to realize that Lenz's law says the direction of the induced EMF is in such a way that when it produces a current, that flux that it will produce would be opposite to the change. That's what the negative means. So let's start there. Let's start there with direction. If I pull this metal bar out, what that would tell me is I would get more and more flux inward from the primary field. The secondary field then would be set up in such a way to oppose the change. So how do you oppose the change? Well, you make a field coming out. So if you have a loop of current that is making flux come out, then what direction would that current be? Well, that's where our right-hand rule comes into play here. Pointing my thumb out means my fingers would be curling around in a counterclockwise direction. And so in this resistor, they show a current going down. And that would be the direction of the current. Yeah?
Wait a minute. So if the current if the resistor was not there and you pull the bar, and if the whole of the superconductor, would it function like a spring because as you pull the thing out, you produce a current, but the current was not dissipate and produce a magnetic field, and we remove the force, it'll spring right back to where it was? No. If I were to pull this out, it would produce a voltage. The voltage would make a current. Now, if there's a resistor, yeah, but, okay, if there's a resistor, then that energy, that current, is going to dissipate and become heat. If there's no resistor, if it's a superconductor, then we just have current. And would it spring right back to be like no limits because of the current that will push back?
Why would it? No. Why? I mean, what force?
Because there's magnetic fields in there, and it probably pull right back.
Okay, let me keep going with this. Hold off on that. I think you're going down the right direction here, but let me add to this. Okay, but look, just focusing on a direction here. So this is being pulled out. The one that I inadvertently put up there first was the second one that I wanted to look at. Is what about if it went the other way? Again, before we get into the calculations in terms of the number here, in terms of the voltage, let's just answer this question: what direction is it? Because this could get a little challenging. So again, remember primary and secondary effects. So the primary field are these these green X's going into the board. They don't even give me anything in the picture of where it comes from. I guess I'm kind of thinking it's this giant horseshoe magnet like this one here. And so they've got it going in. So if I took my North Pole and held it this way, then what they're saying here is this whole experiment is done inside of here. There is a primary field coming somewhere else, okay? Don't confuse that with the secondary field. And that's what I've noticed in the past. I'm kind of warning you about. There's a couple of effects going on here, and you got to go through cause and effect and don't mix the two fields. But I would say this primary field is coming from an external magnet. So then,
if I take the bar and I move it in, then what would you say about the flux in this rectangle? Okay, it's decreasing, right? I have less. And what Lenz's law is saying is a voltage would be produced, a current would be produced, such that the flux created by this new current, what I will call the secondary effect, the flux created from that would oppose the change. So always pay attention to the change. So again, as we go in, there is less. So to counterbalance that change, the secondary field wants to be in. Because we're losing flux in. And so I should get my thumb pointing in to make up for the loss of the flux. And so the current should go around in a clockwise direction in this scenario, which of course is opposite of what we saw before. Yeah.
Does the current also approach zero as the area gets smaller?
Well, it's based upon not the area, the change in area, because it's based on the change in flux. So it doesn't matter where this thing is. And we'll do some numbers here in a moment. But please remember, I think this is one of the hardest things about Faraday's law, is it has a big visual component. And the part you need to visualize is the change, not the flux. So it doesn't matter if this thing is close or if it is far. If it moves 1 centimeter in 1 second, it changes the same amount of flux regardless of where it is on here. And so no, to answer your question, it doesn't matter how close it is. Okay? I suppose you could argue once it's on the other side, it's off the rails. Okay, then we're not going to...
Once it's on the other side, it's going to go this way.
If the rails went that way, yeah. Yeah. In this case, we'd run out of rails, and we wouldn't have a loop, which I might point out. I was going to wait a few minutes, but as long as you're adding to this, what would be different in this scenario if there was no resistor here? We would get no current, but would we still get an EMF? Yes. Yeah. And so you still have the voltage, you just don't have any current, and because you don't have any current, you don't have a secondary flux. But you can still go through the right-hand rule to figure out what direction the EMF should be to produce that current. I think your author does a good job when he puts in this picture, it was a little bit earlier, he did it together right here. He said, think of it this way, that as this bar gets pulled outward at some velocity v by some applied force, then more and more flux would be coming in. If there is a resistor here, then there would be a secondary flux created. That would be, let's see, more and more, so we got to oppose that change. So I'm going to point my thumb out. We would have a current this way. And that can be thought of as that there is a voltage produced. And so we quickly take our changing flux, we replace it with a battery. We take the battery and the resistor and we calculate how much current. Once we calculate how much current, we go back to chapter 30 and we calculate the strength of the field from the secondary effect. Does that make sense? So we're going to put all this good stuff together. And these problems are going to be very long and very detailed. But there's only one thing new in this chapter. And that is a new way of getting the voltage. And so as I mentioned last time, hopefully when this semester is done, you will make sure that you can share with everybody at Thanksgiving dinner. Yeah, there's 2 ways to produce a voltage. There's 2 ways to produce a field. One is by charges, and the other is by a changing magnetic field, a changing flux. That's the second effect. And the more advanced effect, and the more complex effect. And it's too bad we're getting to it finally at the end, because we're just ready to get some really good stuff. But that can wait until next year for those of you who go into electrical engineering, applied physics, or whatever. And you guys who do your mechanical thing won't have to worry too much about that. Yeah, you just have the concept here. All right. So this is replaced with this. All right, so now that I hope you got the direction pretty good, let's go to the number. What would be the value of the EMF produced here? And so I'm going to come over here and start working on these. Okay, this is the EMF. And again, I'll just put absolute value. I'm not going to worry about whether the voltage is positive or negative. The direction of the voltage I can get by using my right hand and using Lenz's law. Okay, so that's going to be one way of the direction. I'll just get the magnitude. The magnitude would be this number of turns times the change in flux. Let me write out the equation for flux. And so you might remember last time we got started here and said, you know, the flux calculation is really in chapter 30.5, but let's look at it now as we go to apply it here. And that's what we need to do in this case. I'll start with this N. What did this N mean? Number of turns. Number of turns where? You see, I point that out because in this one, it's not too confusing. It's the number of turns I have here. It's the number of turns what I will call in the secondary. The number of turns that, you know, is where I want to calculate the voltage at. And what I was trying to show you last time when I had my magnet and my wire, I kept looping it around. And so this is the voltage I would get from one loop. This part right here, that's one loop. So if I wrap it around many times, I would have many different voltage. And so maybe I should put a little S here. And the reason I point that out is because remember, there is a magnetic field coming from the primary. And in this picture, we don't really see it. And I held this up saying, well, the field could have come from a permanent magnet. But couldn't that field have come from something like this? And so this has many turns. This could be creating that primary field. And so there would be a certain number of turns here. That's not that N. This is the N that is used to create the primary field. And that, don't get me wrong, that may come into play. Because that number of turns in the primary is probably going to show up in here. And so it will come into play. But that's not what this one means. And so that's why I say be careful here, because there's a lot going on. It's only one new step, but it can get pretty complicated when we add it with the old stuff we've been doing here. And so you guys are right that I would put the number 1 here because there's only one turn in my secondary. And I don't even know how it's coming from my primary, so I'm not going to have to worry about that. But let me go on and write the derivative and then do this integral. E dA cosine of theta. Let me start there. And you can see why I picked this one to do first. It is certainly one of the easiest ones here. What are they trying to say about this angle and this magnetic field? Yeah. And so the angle is 0, right? The area vector points perpendicular to the surface, so it's out or in. I'm not going to worry about pluses or minuses. And then the field is in. And so you can write this as cosine of 0 degrees, or you could write it as cosine of 180 degrees if you want. That's just a plus or minus 1. That doesn't really matter when we're talking about the magnitude of the voltage anyways. So that one goes away. The other thing that I hope you noticed in here is that they gave us a fairly simple one in the sense that the magnetic field is a uniform. They mention it in the problem. I should have mentioned it too, but they illustrate it in the diagram by making the spacing between each of their flux lines the same. And what's nice about that is I can pull it out in front of the integral because it does not change over the area of that rectangle. And then what I end up with is the integral of just A, and that's
just the area. Now, the area, looking at this diagram, would be this position x times that length L. So I will write it as Lx. And now the final step is to take the derivative, and hopefully you can see that these first two do not change with time. The part that changes with time is the position of it. And so I would represent that with a v for velocity. And so there is the EMF that is produced. And that's why the author had over here, the magnitude of the EMF is the field times the L times the velocity. And so there's my first calculation of my EMF. I got direction and I got magnitude. And that's what's new. If I take this one step further, maybe we can tie it together with the past chapters, because that is going to make some of the problems you do more of the challenge, is tying together this new stuff with the old stuff. So let's keep going. Could you tell me how much current is in that loop? Well, take the voltage and divide it by the resistor. It's the easiest circuit you've ever worked with, right? It's one voltage and one resistor. Okay, that was way back in chapter, 27, the easiest thing we had there, Ohm's law. So that would be the current. What if I calculated the power dissipated in that resistor? What would I have there? Yeah, okay. I squared R. So if I square I get a B squared, I get an L squared, I get a V squared, I get an R squared times another R. And a couple of those R's go away. So I get B squared, L squared, V squared over R. And so if I was asking how much power, or what rate is this resistor warming up, if you will, there would be the equation. Now let's tie this together with even some other things that we've learned from past chapters. I'll leave this here on the board, but you've just told me then that as this thing gets pulled out, it produces a voltage. That voltage is in such a direction that it produces a current that is in a counterclockwise direction. If there is a current in a magnetic field, wouldn't there be a force on it? So let's take a look at each section of this rectangle and say, aren't there forces on each section? For example, the place right here where the resistor is, isn't the current going down? Didn't we learn that if you had a current in a magnetic field, there would be a force? So if I take my right hand and I put my fingers down and I close it towards the magnetic field, which is in, wouldn't I get a force inward? So isn't this resistor being pulled in? Isn't this part of the rail being pulled up? Isn't this part of the rail being pulled down? And perhaps more significant, what's happening to that one, the one you are trying to move? Current is up, field is in, force is inward. And so your author has put right here that there would be an inward force. And so as you try to pull it out, there's going to be an opposition to it. It kind of makes sense, because if there was no opposition, if this was just physics 121 and I came over here and said, hey, let's do some work. Let's take the applied force and move it a distance x, wouldn't that equal to the change in the kinetic energy? Wouldn't the rod then be going faster? And so that applied force would show up as kinetic energy. But in this case, something quite interesting happens here. As you pull it, and as it goes faster and faster and faster, the current gets stronger and stronger and stronger, right? As it goes faster, the current gets bigger. As the current gets bigger, no air resistance here. Leave that alone. That'll just make it even harder.
But as you pull on this thing, there's going to be an upward current. That upward current is going to make a force going back. And so as you pull, you're going to, whoa, wait a minute, something's pulling back. And at some point, the force pulling back could build up to the same as the force pulling you forward. And in that case, what's the net force? 0. And what happens to the rod? Okay, it doesn't stop moving. No, you didn't say that. I didn't hear that. It stops accelerating, exactly. The net force is 0. It stops accelerating, and it keeps doing what? It moves at a constant speed. Let's say that happened. Let's say, then, we get to the point that we have pulled on it, and it gone faster and faster to the point that the induced voltage gets enough to make enough current so that the magnetic force pulling back are equal. And what we mean by that is then the force would be equal. The applied force would be the same as the magnetic force. And so my question for you is, now that you are doing work and pulling, you are applying the force, does that work show up as kinetic energy? Where does it go? You're still pulling on it. Where does that energy go? Creating a current, which then creates heat in the resistor. And so what you have is a mechanism here of taking some kind of force that you pull on it and converting it into electrical energy, which then converts it into heat energy. Let me leave that up here because, again, if I take what is new this chapter together with old chapters, this one here, and our old mechanics here from Physics 121, plus our chapter, whatever this is, 29, or 28, no, 29. Let's look at this one a little carefully. How do you calculate the magnetic force? Isn't this the magnetic force? At least if you have a constant field and a constant length and a constant angle. If it's not, we got to integrate it, and that's what we did on the second part of number 5 on the test. First part, it was just a straightforward calculation here. So this should be I, this should be L, this should be B, this should be the sine of 90 degrees. I mean, maybe I should apply that. As I now realize, there is a current in here, and the current's going across here. This I cross B gives me this magnetic force. And my point I'm trying to make is, if I've already got it moving pretty fast, then these two forces are equal. The net force is 0, the velocity is a constant, and the force would be equal to this value right here. The length of the wire would be L of the rod. The current that is produced is the current that is coming from over here. So I'm going to put a B, an L, a V over an R, and I'm going to multiply it by an L and multiply it by another B. That would be the equation for the force that I am getting magnetically, which should be the same as my hand. How about the power that my hand is applying? Now again, we need to go back to Physics 121 here, but the power is force times velocity. So if this force that I am getting magnetically is the same in magnitude as the force my hand is applying, and I multiply everything by V, this, I would say, is the power that my hand is producing by pulling on it. And it should be equal to, let's see, B squared, L squared, V squared over R. Hopefully not too surprising
that it actually comes out to the same power that is being consumed by the resistor as it makes a current and produces heat in my resistor. And so what is happening is a little bit different than something without any electronics or without any air resistance. Without any air resistance, without any electronics, what happens is all this work that I do becomes kinetic energy. In this case, all the work that I do doesn't become kinetic energy. It doesn't go any faster. Where does it go instead? I guess it first becomes electrical energy, which then becomes heat energy in the resistor. Yay! Wasn't that simple? Okay. And all because I've got a little rod that is moving along here. All right, well, these take a while to sink in, no doubt. So let's look at a different one. How about we look at a rod spinning in a magnetic field instead of a rod translating in a magnetic field? Would this produce any voltage? Ah, okay. Maybe it's worth going back to the picture before. Okay. Not that one. Now, let's address this again. All right. So, if I understood this right, here's the whole cause and effect. By me pulling on this, I give it a velocity. By giving it a velocity, there's a change in flux. A change in flux produces an EMF. An EMF then produces a current, but only because I have a closed loop. Now, that current then, of course, creates heat in here and creates a secondary magnetic effect. But I think what you're pointing out is, what if this resistor was just cut out of the way? Not even there. Would you get any current? No. But would you still have a voltage? If you took this circuit and cut out that resistor, don't you still have a voltage? But you don't have any current, right? And so because you don't have any current, you also don't have a secondary magnetic field. But I want to emphasize, do you still get a voltage? Yes, absolutely you get a voltage. So the voltage part of it is produced because of the changing flux. Whether that voltage results in a current is just like we were doing in chapter 29 when we took a battery. Once we take a battery, we get a voltage. Now, whether that results in a current all depends as if we hook it up to a circuit. If we do hook it to a circuit, then we will get current. And how much current we get depends on how much resistance we hook to it. And I'm trying to say the same thing here, that if you were to pull on this and you did not have that resistor there, in fact, if you didn't have the rails there, if all you had was an airplane wing flying through the Earth's magnetic field, you would get a voltage from one tip to the other tip of the airplane wing. You're not going to get any current because you didn't hook a wire to the other side. But you are going to get a voltage. And so anything that's moving in a magnetic field is going to produce a voltage. And an airplane flying over the Earth is going to make a voltage from wingtip to wingtip because it's in a magnetic field, because it's moving. It's not going to produce any current because you haven't set any wires to loop around it. But if you did, you'd get a little bit of current. Naturally, you'd have to, well, I'll leave that alone there. But the idea is still there, which is why your author follows up that first discussion with this discussion. Let's take a bar and let's change two things. One, we change from translational motion to rotational motion. And two, we take away the connecting wire here. But maybe for discussion, we should say, if there was a wire connected here with a resistor, then as this thing rotated, wouldn't there be an increased flux inside of there? And so if this had a resistor right here, when it moves over to here, I would get more flux going in. So there would be a secondary flux created to oppose that change. Fair enough? But your author on this one, excuse me, says, let's do this one without a resistor. There would just be a voltage. And so if you took a voltmeter and you put one connection there and one connection there, you would get a voltage from one tip to the other. What would its value be?
It would vary along the bar because
Well, I agree that it would be based on the length of the bar, but wasn't that true for the one that we just did? Maybe I'll put it back on the board here. The one we moved, which was just translational motion, we had this. The EMF is equal to B, L, and V. Doesn't that say that the EMF depends on three factors? One being how big is the magnetic field, the other one being how long is the bar, and the other one being how fast is the bar moving. And all three of those factors together determine what is the voltage. So yes, when you say it depends where you touch it, oh, absolutely. The length of the bar is hopefully the obvious point. From here to here would be a different voltage from here to here and here to here. But let's go the whole length of the bar. Could you give me a formula for the whole length of the bar that would give me the voltage? What do you notice about this? How is it related to that, but how is it different? Yeah, the real key, if you remember from our mechanics here, is when you have something rotating, each little section is actually moving at a different translational speed, isn't it? The same angular speed gives you a different translational speed. So let's do this. Let's take our brilliance of our calculus and say a little EMF is produced for a little bit of length of wire. And so each little section, and this is what your author is trying to illustrate right here, that little section, which he labels as a DR, would produce a little bit of voltage. So using his notation, I will change this to dr times V. And basically what he's trying to say here is you can take this bar and break it into little tiny pieces. The total voltage would be each little piece added together. It would be like we did in chapter 29. Stack your batteries together. If you have a 1.5 volt battery and you put another 1.5 volt battery together with another and another, like you guys do in your calculators all the time, you put in 4 batteries, you stack them together, you get a total of 6 volts. That's in here is let's get the total EMF. The total EMF, E, is to add up. Add up the voltage I get for each little chunk. And I am going to then start at the beginning part, which they label it as R equaling 0, going to, do they label the whole bar? L, okay? And so L, the whole length of the bar again. And of course, what makes it a kind of an interesting calculation is this part right here, V. V is the velocity of each little chunk. Okay, well, each little chunk would be related to its angular speed by an omega r. And so the B and the omega are the same all the way throughout this bar. Uniform field, I'm assuming here. It's spinning at some angular speed, omega. And now I just need to add it up. And so I get a B, an omega, an L squared over 2. And so there would be the equation for the voltage produced from a helicopter blade as opposed to an airplane's wings as it spins in the Earth's magnetic field. And so there'd be a little bit of voltage there. You guys are quiet. Is that good or bad?
Well, it was more than enough in magnetic fields for things that are still, now they're spinning.
Oh yeah, you are right.
If the pivotal point is on the center with the EMF be 0,
If the what?
if that dot O is right on the center with the EMF is 0.
Yes. Yes, I guess it would be. So, well, I guess it depends, though, on how you set it up. I mean, for those, he's asking if it was spinning around its center, what would you do? If you, I guess, if I wanted to produce some voltage, what I would do is I would take my wires or my voltmeter, and if it was spinning around the middle, I would touch one in the middle and one out here, and then I would get a voltage. But if I were to touch each of the ends, then the voltage from here out cancels with the voltage from there out, and so it would be like I have two batteries, one going minus plus and the other one going plus minus, and they just undo each other. So the net voltage in my circuit would be 0. Yeah. Yeah. All right. Well, I'll keep going because I think the best thing to do is just a lot of examples to have this sink in. Yes, question.
Which way is the EMF going on that rod? Is it going from minus to plus, or I'm confused on what is that even saying?
Oh, so yeah, which is the higher voltage is what you're kind of asking here, right?
So I guess towards the end of the rod you have a higher voltage than the beginning.
Well, maybe I'll kind of draw a picture here. I know it's not really hooking up to a wire, but that's the best way to view it. What if I actually hooked it up here? Okay? Because this is where the Lenz's law comes in. As this thing would then move, say, to here, that would go and produce, let me say this right, more flux into the screen, right? And once I have more flux, the secondary flux then is going to be created to be outward, to balance it. So I guess the current would flow this way, meaning this would represent a positive and that would represent a negative. Yeah. Let me see if I'm getting that right. As long as you bring it up, there's another way of viewing this, which doesn't illustrate the math I wanted you to see, so I didn't do it, but your author does. He says, you can view this as, remember, this metal bar has billions and billions of electrons in it. And so when you spin the metal bar, these electrons are moving in a magnetic field. And we learned that there was a force, we called it a Lorentz force here, on charges that are moving in a magnetic field. So knowing that the field is in, I could say at this moment right there, the electrons are moving this way, the field is down, so V cross B is this way. Now remember, they're electrons, so the electrons are going to be pushed that way, which means then the current is that way, which fortunately matches what we just did here with Lenz's law, which it ought to, but I wanted to make sure it did. And so we can maybe look at this a little bit different in terms of a molecular level. But when you do it this way, you don't get a chance to calculate any change in flux, so I didn't do it that way. Yeah?
If the wire was pulled at the anchor point and it was moved after the flux, it would produce a certain amount of current.
Here? Like that?
Yeah, and its opposite number going from the anchor point to that center. Okay, which of those two would produce more current?
Well, this one, this end of the rod has a lot more motion than that end of the rod. Yeah, yeah.
It's also because it covers a lot more area, right?
And okay, and if you're looking in terms of flux, as you are swinging through, you would be changing a lot more flux for the stuff that is further out, because as you said, it would be covering a larger area out near the end of the rod. Right? Yeah.
Wait a minute. What if the loop doesn't? The way you drew the picture, it looks like the loop extends out a little bit. What if the loop were to follow along with the reservoir were to follow along with the rod?
Well, okay.
No area changing. There's feeling of the velocity.
So you're saying do that, right? Or what you're saying, move it along with it?
Yeah.
Okay, so if I move it along with it, right, so there would be no change in flux, and there would be no EMF, and there would be no current. You could view it as saying that because this rod is moving, this end of the rod would be a plus and a minus, but because the wire is moving, this end would be a plus and that end would be a minus. It would be like taking a battery and an identical battery. How much current do you get? None. And so each of them are moving. So, yeah, that's, if this one's moving along, forget it. You're not going to get any voltage. That's why I got the impression after I mentioned airplane wing flying through the air, people are thinking, ooh, and could we use the voltage to generate electricity to run the plane? Well, no, not if the thing you want to run is moving along with the airplane, because you end up with the airplane wing moving and the object you are trying to use that electricity for moving. Now, if you had an airplane that was moving, that had wires connected to it, and those wires went down on the ground, and so the object on the ground wasn't moving, yes, then you could power that thing on the ground with the movement of the airplane, but not when both of them are moving. They just each produce an EMF and get no net current. They just each produce a voltage opposing each other, so bummer. So, all right, let's look at this one here. This one I think really answers the question, so maybe I'll go quickly with this one, because this one has a loop right here, and the loop starts outside of the magnetic field and goes in, through, and out. When do you produce a voltage? When it's outside the field? When it's transitioning to inside? When it is completely inside? When it is transitioning to the outside? When it is completely on the outside? And hopefully you'll see all 5 sets, because I would say that while this rectangle is moving out here, how much change of flux do you have through it? None. And in fact, this graph A says let's plot flux with position. And so they got a bunch of no flux. But as it transitions into the field, and so in this area here, at 0, the flux begins to increase. And that's what this is showing. Increase, 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 increase. But once the entire rectangle gets inside of the field, so somewhere in this area, as it moves through the field, what is the change in flux? None. And we're back to kind of this scenario where you could say you have a single rod moving, but another single rod moving. And so this rectangle, this part is making a voltage, and this part is making a voltage. And you get no net current in there. You have no change in flux. And so this graph shows constant flux until you start to come out. The EMF, as shown in this graph, is the derivative of the flux. And so the only time you are going to get current in that loop is when you transition. And so in this case, they show that this part here, there is a derivative. Here, the derivative is 0. Here, the derivative is non-zero again. Now, they put pluses and minuses, and we can debate that if you want. I'm not going to worry about plus and minus. I do want to go back to Lenz's law and ask what direction is it. So, as this rectangle, and maybe I should backtrack for summary, when do I get a current? Only when the rectangle here is going in or coming out, right? Then I would get a small amount of current. And that small amount of current would be what direction right here as it is going in? Well, let's see. As it is going in, that is increasing the flux into
the rectangle. Fair enough? So to oppose, more flux going into, the secondary flux would be out. And so as I point my thumb out and wrap my fingers, I would get a current in that direction, which is a counterclockwise direction. And for whatever reason he calls it negative. I would be tempted to call that positive, but he calls it negative, yeah.
How strong is the primary flux versus the secondary flux? Does it actually cancel it out?
If there was no resistance, yes. The way this is set up exactly would match. And so it would cancel out the flux. Yeah, yeah. But of course there is some resistance, and so what ends up happening is the first, you might say, moment in time, it completely cancels it, but then it dies away and the flux does actually increase up. So a better picture of total flux, this is just the flux from the primary. A better picture of the total flux would be it'll stay kind of flat here for a while and then arch up, because you have the primary and the secondary. The secondary is opposing to it. With no resistance, the total flux would just stay the same all the way through. Yeah.
Didn't you just say there's no current produced if there's no resistance?
Yes, there would be current produced here. And what would be different here is if there was no resistance, as this thing moved in, you would produce a voltage and produce a current as you're going in. Once you're all the way in, you're not producing any more voltage, and so whatever current you produced remains. And as you pointed out, it would produce enough current so that the flux coming out from the secondary equals the flux coming in from the primary, and so you would have no flux there. And then as you go out, the EMF would be the other way around, and then all that current you produced is now stopped, and by the time it gets out the other side, you would now have no current. All right. Well, anyways, I think you kind of see this idea. We should probably do the part that's going out also. And so looking at it going out, as it goes out, now remember by this time it's already been in, so there's already lots of flux in the rectangle. And so as the rectangle is moving out, we are getting less flux inward from the primary. So to make up for that, the secondary is going to produce flux in. So I'm going to take my right hand, point my thumb in, and my fingers are then going to curl around in a clockwise direction. And so they represent it with a positive number there. Definitely they're opposite directions. One direction, one the other direction. In case you missed this, this is big. The world we live in, every time you store something on your computer, how is it stored? How is it read back? It's magnetic. Let's pretend that I have what you might call a reed head. It is a giant coil. And over here, maybe on this surface, I have a spinning hard drive. Spinning hard drive. Why do I have a spinning hard drive? Moving magnets make electricity. Exactly. I need the magnet to move. And so if I had a surface, a magnetic surface, now granted it's very microscopic in size, but if I had a surface here that was magnetic, and I had places where the magnetic field is pointing up and places where the magnetic field is pointing down, and I take something like a coil and I hold it here and the hard drive spins underneath it, what happens in this coil as the little magnets move by? This. You get little pulses of current. You get a little pulse one direction and a little pulse the other direction as the magnets move. And the pattern of those magnets that are on my hard drive, billions and billions and billions of them, will make a pattern of little current that goes to my electronics in my computer. And so when I want to get that document that I've been typing all night and it's time to print it up in the morning, and so I typed it all night, I saved it, I went to sleep, I got my standard 2 hours of sleep like all good physics students should get, and then I wake up and then I go to recall it. what's going to happen is that hard drive is going to spin, and it's going to go through there, and it is going to bring it back. And so it's a Faraday's law is what the whole world seems to love to do. We have all these moving magnetic stuff. You guys, I don't know if you guys, are you old enough to remember the VHS tape? The audio cassette tape? The 8-track cassette tape? Oh, a couple of you. The reel-to-reel tape? Yeah. But all of those are magnetic. How about the little floppy drive? Remember those? All of those had some kind of magnetic material that moved. It moved next to the read head. Now, coming back a chapter, the opposite is true. What happens when you are trying to save the file? The hard drive was spinning. There was probably nothing recorded here. There was no magnetic fields. And this same little coil right above the surface, the computer put current through it. And when it put current through here in a certain pattern, didn't that make a magnetic field? And what did that magnetic field do to the magnetic material? It made the magnetic material flip and change into a magnet. In the same pattern, billions and billions and billions of little magnets of the same pattern of current that the computer put in there. So that later on, when the magnetic hard drive goes by, it will produce the current in exactly the same pattern that the current was put in here originally to make the little magnetic field. And so we just put it on the magnet for safe storage. So someday later we can send it by the coil and get that same current out. And so that file that we saved the night before, when you get up and call it back up, it loads back up, and now we have it, and now we can print it. Oh, a bunch of questions, yeah.
How do solid state drives work if there is no spinning or anything like that?
It's not Faraday's law. No.
Is it something we'll learn in this class?
No. Yeah, no. So yeah, I'll hold off on that one. Yeah.
So you said to store a magnetic field onto some hard thingy.
Kind of. How's that? Okay. Yeah.
So to magnetize something, you said you need to spin the electrons.
Not to magnetize it, but to get the current to be read from the magnetic material, I have to have a change in flux somehow. The change in flux can easily be produced by the hard drive spinning.
Yeah, but how do you take like one piece of something and have different magnetic fields on each part of it?
Well, remember, if this is, some kind of soft iron, okay, there's billions and billions of atoms. So if I just take the first million of them and make them go in one direction, I'd get a little magnet. But it's only the first million. That's small. Because then if I take the next million, I can point those atoms in the other direction.
But didn't you say eventually they will actually equalize each other?
Oh, yeah. So I hope you don't plan on storing this thing magnetically for 100 years. It won't last. You might even have some question after 20 years. Yeah. Those of you who are old enough to pull out those old audio cassettes, you'll notice it right away. Put it in the little player, put it down. Hey, what happened to this great music? You know, it used to sound so good in the 70s. Well, it's not magnetic. Yeah.
Wait, didn't you say earlier that with the bar problem I mentioned earlier, that superconducting wire thing, if you were to pull the bar, it would you said there would be no current produced if there was no resistance. But here you say, oh, there is a current, even though there's no resistance whatsoever. So.
What?
Remember earlier when you showed
Yeah.
us the loop that we were pulling the bar a while back?
Yeah?
You said I was asking a question, what if the whole thing was a superconductor of some sort? And
Yeah.
would a current be produced?
Yes, it would be produced.
And if you were to let go of the bar, would it, and because of the current, if you let go of the bar, would the bar go back to its original position because there's a current there?
I guess so, if I let go of it, yes. Because what happens is I pull it, I would create a current. That current would create a force going back in the magnetic field. So when I let go of it, now that I've pulled it, that force pulling back is going to slow it down. And would it stop it? No, I think it's just going to stop. I don't think it'll pull it all the way back. It will slow it down. No, maybe it should. Well, I'll tell you what, I'm not sure about that. Why don't we talk about that in lab and office hours here? But I want to keep going here. All right, watch this one. If those made sense to you, let's try another one. Let's see, what picture is this? I got, let's try this one. What if I took, and that's why I brought these out here, I've got a coil here, I got a coil here. What if I were to take this, and in this case, turn a couple things off here, but let me just take this and send some current to here. And let me do this. Let me take a single loop and put it around that solenoid. Is there an EMF produced? Well, let's give it a try here. According to Faraday's law, if there is a change in flux, there would be an EMF.
Oh wait, does the current changing, right?
So the question really comes down to you visualizing this flux. The flux is produced by the current. Let me pause right there, because this actually takes us back to chapter 30 here. Let's calculate the flux from this solenoid. And so ignoring the, they have a blue loop here, but let me just take that solenoid there and say, all right, how much flux do I get from that solenoid? I'll start with the dot product. And the reason I picked the solenoid and the loop here is here's this blue loop on the outside. What is the angle between the flux and the area of that blue loop? Which way does the field go from a solenoid? Along the tunnel, right? Now, which way depends which way the current is going. In this illustration, they're saying the current keeps changing direction. So the field's going to go to the right and then the left and then the right and then the left. And it's going to keep changing. But it's going to be along the axis of the tunnel. All right. Knowing that, then, the angle between the flux and the area would be 0 degrees. More than that, and the reason I picked the solenoid, is we know that within a solenoid, the magnetic field is a constant all the way through. That was our lesson from chapter 30. So I'm going to pull it out. And so then I just get the magnetic field times the area. How do I get the magnetic field from a solenoid? Isn't that the equation from a solenoid? Now I want to make something really clear here. That this is the current going into the solenoid. I'm going to call that the primary effect. Right? This is the current coming from this coil. Because I could then perhaps get a current
in the secondary. And so I don't want you to confuse the current and the flux in the secondary with the current and the field in the primary. So I'm going to put a little P under there to say, look, the field is created by this guy. I'm kind of asking how much current will it produce in this guy, the secondary. Well, right now I'm just focusing on the primary. What would the area be? The area of what? Is it the area of the blue loop or the area of the solenoid? Well, what do we learn? About solenoids. So do I do a little r or a big R here? Big R. Why big R?
Oh, yeah, because that's...
The flux is coming from the solenoid. Where is the only place you have a field in a solenoid? In the tunnel part, right? I mean, granted, I am interested ultimately in what is the flux through the whole secondary blue loop. But because I only have flux where the solenoid is, the rest of it has no magnetic field. So when I go to calculate the total flux, given that the flux is only coming from the solenoid, I would want a capital R here and not a little r. And so that would be the flux through my solenoid. And that, I should point out, has nothing to do with this chapter. That last chapter, right? Which I shouldn't say have nothing to do, because the whole reason I wanted that is now how do I get the EMF? Take the derivative. Yeah?
Can I ask what's the direction of the magnetic field? Because you write is 0. Cosine 0.
The direction of the magnetic field. Remember, in a solenoid. The direction of the magnetic field is along the axis. It's either this way, if the current goes around like that, or it's this way. All right, so, all right, fair enough. If you want to put that, then I either have a plus or a minus. And I'm going to calculate the magnitude of the EMF. And so my EMF is going to, as you'll see, if the current changes, is going to go plus, minus, plus, minus, plus, minus. And there's no point in defining which one's plus and which one is minus, because that's just a matter of where you start your axis. Start your axis wherever you want. So a sine function, and a negative sine function, and a cosine function, and a negative cosine function, that's just a matter of reference point of where you want to start it. Oh, right, so this says right here that the current is changing with time. So it's going to go one way and then the other. Plus, minus, yeah.
Would you just clarify really quick, what is that angle again?
It's 0 or
No,
180.
Between what? The magnetic field and what else?
Dot product between those two. Magnetic field and?
Okay, but isn't the area in 90 with the magnetic
No.
field in this case?
All right, so here's the secondary. What direction is the area vector? Perpendicular to the surface. Right, there it is. So the area vector is out or in. The field is out or in. Okay, but either way it's either 0 or 180.
Oh, yeah.
Okay, so not focusing on the 0 or 180, because again I'll just do magnitude and I can do Faraday's law here on figuring out direction. I can then get the EMF by saying it is N d phi dt. Now, what N is this? Yeah, let me call this N secondary. This would be the number of loops that the voltage is being induced, which the way I'm holding it up is 1. And so this guy says on here 180. So the primary has 180 turns in this. And the secondary has 1, the way I've got this one set up. And I'll just leave it more general and write it as secondary. And then I got to take the derivative of that thing. All right, so I'm going to take the derivative. I've got the mu naught. I've got the turn density of the primary. I got the current in the primary. And I got the pi r squared. I'm hoping you can see that as I go to take the derivative, the only thing changing with time is the current. And hence, that's why I do have a changing flux, and that's why I do have an EMF. If the current, I think some of you were pointing out, if the current was just a constant DC current, this doesn't change, then what do you get for the EMF?
Nothing.
Nothing, right? I've got to have something that changes it. And so, as I've said many times, this is the answer to all the homework problems you're going to do this chapter, but it does get quite involved where you have to look at how is the change flux, the flux changing. Is it coming because the current is changing? Is it coming because the angle is changing? How is it changing? There's a lot of options here. So we need to put this together with our past materials, and you can see that the problems can have a lot of detail and be kind of lengthy. And so it's kind of like telling somebody, this is an easy chapter. Running a marathon is easy. All you got to do is take one more step. But there's a lot of steps, and it's not that easy to finish the marathon. But that's essentially what this chapter is about. It's just hey, one more step. That's all it is. Guarantee. You'll be done. In 15 hours, you'll do the first problem. Just one more step.
So normally we're dealing with a change of value. This one is just a change of direction.
No, the current changes direction.
Going and coming back.
Oh, yeah.
With the same magnitude, but different direction.
Right. And so as the current is changed, let's go back to here, a flux. So this is the flux right here. And that number is changing. So as that number changes, then the flux changes. And if I were making a plot of the graph of flux, because that changes, it's going to go like this.
Oh, so it does go smoothly because it's actually raises and goes down.
Oh, yeah.
It doesn't just...
This is a continuous function, you would say in math. Oh, no. It's not like I turned it off and turned it on. Yeah. Okay, so again, going through some of these numbers, I would get NP, I got my pi, my r squared, and then I've got the derivative of the current. And maybe for completeness, I will put n of the primary times the length of the solenoid to maybe emphasize that the turns in the primary are important and the turns in the secondary are also important. They show up differently, and so make sure you keep your numbers straight, which is the primary and which is the secondary. But the original field created from the primary has number of turns, and the induced voltage shows up in the secondary. And then in this case, they say that the current is some maximum amplitude times cosine of some frequency. So when I take the derivative I get my maximum current. I also get an omega, because the derivative of a cosine is it's a negative sign, isn't it? But since I've already been ignoring pluses and minuses, can I do it again and feel okay? And so there would be the equation. A lot of pieces to it by the time we put everything together. Side note, for some of you, for the rest of you, to get you ready for next Tuesday, if we put all of this together and called it L, we will hopefully see that the voltage
is proportional to the change in current. We will call this L for inductance. You guys done inductance in circuits yet? And that's what you've been talking about. Faraday's law. Faraday's law is the voltage that is produced in that little coil because of the current you put in that little coil. And so it's Faraday's law. And we will do that inductance in the next chapter. So good thing about next chapter, we won't learn any new physics. We'll just apply Faraday's law to our circuits. Okay? Now, if you're good with that, maybe I can even illustrate it. Here it is. I could turn this on. Oh, I guess it already is on. And if I were to hold this right here, I would say that there is then an induced voltage in here. And whatever the resistance is would produce a current. If I were to take, instead of just one loop and 440 loops, so 440 in my secondary, 180 in my primary, kind of feed them together, then I claim, whoops, looks like it's unplugged. I claim that there is a voltage then right here in my secondary. To convince you of that, I will feed it to a small amplifier. Because the voltage will not be much, I will then amplify it and send it to a speaker. To convince you it is induction, I will separate them. And now this solenoid, which is producing flux, is too far away from this to have any flux change in here. As I get it closer, a little bit of flux. If I get it closer, a lot of flux. If I get it close and turn it, I get no flux through it. The direction of the flux is important. And how much flux? And yes, it is directly connected to this. The frequency of the current I put in is the same frequency that is induced on the other side. And so I have the information going from one to another, depending on how far apart they are, what the frequency is, and what I'm going to induce from one to another. Fair enough? Okay. Shall we look at another one? I'm hoping you're beginning to see these are looking a lot the same. Here is a really, really useful one in terms of today's technology.
That's the basis of the wireless electricity transfer, isn't it?
Yes, that is the basis of the wireless, yes, transfer of energy. Let's take a look maybe at, well, I'll do this one. It's a slightly different picture than what I have up here for you. So maybe I'll switch it out. Take a look at this for a moment. This is supposed to be that loop right there. There's the loop. There are my contact here, my commutator. I'm going to put this loop in a magnetic field. Now, I don't really have a magnetic field. This is just kind of a prop here. But you can see that if I mount this in here, and these were magnets, and I have a north and a south, which looks like this one is kind of the reverse of that one. There we go. How about that? Okay, so I got north over there and south over there. I've got my brushings touching my commutator here. But if this spins, is there a change in flux in this secondary?
Yes, and there will be a change in, there will be alternating current as well.
So will I produce an EMF?
Yes, and this is exactly the way most of the generators in the world are working. The one, every time you plug something in, what you have is you have a loop that is spinning in a magnetic field. And what makes it spin can come from a lot of sources. This could be water flowing through a turbine and therefore generating electricity. We call that hydroelectric electricity. This could be wind blowing and could be turning my windmills. Oh, phone call. It could be, as in most cases, hot boiling steam that turns the turbine, and we just have to get it hot somehow. Sometimes we burn coal, sometimes we burn natural gas, sometimes we burn other types of fossil fuels. Other times we have nuclear reactions that make things hot, and then we just put water on them and boil the water. But somehow we make this thing turn. Like my old college roommate's house, this is hooked to the pedals on a bicycle in the living room. So if you want to watch TV, you have to pedal the bike, which turns the generator, which makes the electricity. So he got really frustrated with his kids watching TV and playing video games all day. So he hooked the TV up to the stationary bike. As long as you keep pedaling, you can watch TV, right? And so you generate your own electricity in order to watch TV. So it's how badly do you want to watch TV is really the idea. And so there's no... All right, but let's run through these numbers. This is a fun one to do in terms of the calculation, and an important one to do in terms of modern technology. It explains, as I was starting this chapter, why all the plugs we have are alternating current. Well, it doesn't tell you the whole story, but it tells you a good part of the story of why alternating current is here, because as you'll see, this will produce an alternating voltage, an alternating EMF. And so, if we look at that and say, all right, here's Faraday's law, the EMF produced is equal to the number of turns in the secondary times the change in flux in the primary. Or the change in flux in the secondary, the field coming from the primary here. And so I'll leave this N sub S alone. I'll take the derivative. And then let's take a look at this rectangle for a moment. How much flux would be going through this loop right here? Well, as I go to, come back. As I go and take a quick calculation here,
Depends on the angle.
I will see a very crucial part here. The angle changes. And so the examples I've shown you had been things like the wires were moving, the current was changing. This is a good example of the angle is changing. So the area of the loop doesn't change, the strength of the primary field doesn't change, but the angle does. And so as this thing is spinning around, the angle does change. So this kind of reduces down to NS derivative with respect to time, magnetic field, area, and then I have cosine of theta. And so as this generator is spinning, I get my N, my B, and my A. And I'm going to go ahead and drop the sub S for a moment because there is not going to be an N that shows up for the primary. It's just a permanent magnet. So the N is in the secondary. And then I take the derivative. Well, what's the derivative of cosine? Sine or minus sine, if it's okay if I drop that off. But don't forget the chain rule. Then it's d theta dt. It's the rate at which the angle is changing. And that, we would say, is the angular rotational speed of our generator. And so we would get an N, a B, an A, an omega, and then of course a sine theta, which I'm going to write as a function of time if it is spinning as omega t. And so what I would get here on a graph for the EMF as a function of time would be a sinusoidal function. And it would go up to and down to and up to and down to and up, and it would go up to this maximum value of NBA omega. And so I would create an alternating EMF. And that's how we produce our electricity in this country, and I think in every country, is they have the little generator and they spin it somehow. And there it is. Now, not all the countries spin it at the same rate. I should emphasize, in the United States, what's this number? Okay, what you meant, I guess, was the frequency is 60 cycles. That means omega is 2 pi times 60, right? And so that's the famous 377 radians per second that you're going to see again and again and again and again and again. Okay? It also comes out to be 3,600 RPM. So don't be surprised if you see a lot of your motors that are 3,600 RPMs. Fans, cooling fans, table saws. The original hard drive and the original CD drive were at 3,600 RPMs. I know now they're like, 24 times or 48 times that original speed, but that's what it means. 48 times the original speed of them. But it's a very simple way of making a motor. Since our generators spin that way, we make our motors spin that way. All right, so keep that in mind. Also, in the United States, what is the total maximum voltage here?
170 volts.
It goes up to 170 volts and then down to negative 170 volts. Don't confuse that with 120. 120 is what you would say, since it goes on, off, on, off, on, off. The power this produces is the equivalent of something being constantly on at 120 volts. And so we'll often say, what is the voltage of our plug? And what we mean by that, 120 is, well, we know it changes, so you don't want me to say all the numbers it has. 0, 1, 2, 3, 4, 5, 6, 7, and then count down and then count up. What is it equivalent to? And so that's how we represent the 120. So when you hear us talk about 120, and you will a lot, because as I said, our next step is to take this physics that we've been learning and apply it. And we're going to get back to electronics and back to circuits in these next couple of chapters here. And there's going to be one more piece of physics before the semester's over, but there's not too much more physics. Now it's a lot of applied, a lot of engineering steps here. What could we do with this? And hopefully you've seen a lot of that today.
Does this generator have to do with the voltage, or does the voltage come from somewhere else? Like for example, in China, it's like 240 voltage or something like that over there.
Oh yeah, so they adjust it differently. I don't know what the frequency is. My international students know.
Like the frequency comes from the generator itself, not something somewhere else. The voltage comes from somewhere else other than.
The voltage is made up of these four factors. How many loops do you put in it? How strength is the magnetic field? What area do you have for your generator? And at what frequency? Now, you don't have much play with the frequency. If you are building a generator for the United States, or the whole North America grid, which would include Canada and Mexico, you've got to set it at 377, hands down. I think Europe is at 50. Any my international students know?
Okay? But I'm pretty sure Europe they have a different frequency, and their peak voltage is different. They do a 240 here, which whatever 240 times the square root of 2 is, so their peak's going to be a lot more. So around the world, they do certainly different things here, but the physics doesn't change around the world, that's for sure. Yeah.
A couple of decades ago, they changed for automobiles, they went from generators to alternators.
Oh, if you spin it like this, I'll give you the short version. If I spin it like this, because I'm always touching this wire and this brushing is always touching that wire, I get the plus minus, the plus minus. I get an alternator. If I remove this one and do something more like this, then as it spins, it breaks contact with one wire and makes a new contact.
So the plus is always on one side.
And I always have plus on one side. If I were to plot the voltage produced by this one, I'd get something that is always positive, never going negative, not alternating, just generating. And so, and there's advantages and disadvantages to each. Yeah.
That was my question.
Oh.
What are the advantages and disadvantages?
Well, most of our electronics, semiconductor electronics, cannot function with negative voltages. The current always has to go in one direction. So as you guys saw in the lab, or at least 2/3 of you, and the other third will do that today, we will take this voltage, convert it first to this voltage, then we will do one more step and convert it to a constant DC voltage. And so a lot of our electronics needs DC. So if we generate it as AC, we got to go through a little bit of work to convert it. So the one big advantage of generating it already with all positives is then you just have to level it out. You don't have to change the negatives to positives.
So why not just go on?
Well, right. So you may argue that if the electrical grid was being set up for the first time today, with all this advancement of semiconductors, that we probably should go to a DC setting. Agreed.
DC kind of like power lossy power lines though? The whole reason the original AC dominated the world versus the DC is because if you generate the power over here and you send it a long distance to the city, your loss of energy along the way is I squared R. So if you want to run a city, you want, in one sense, a lot of power going to the city because you've got to run a lot of people and things. So you either want a lot of current or a lot of voltage or perhaps both. You don't want a lot of current because the current results in the loss along the way. So the way we get most of our electricity, in our case, a lot of it's produced over here at Hoover Dam. It's got to travel 300 miles to get over here to Santa Barbara. And what we do is we send them along wires that are at a very, very high voltage. 500,000 volts. That way, the current can be kind of small. That way, the energy that is lost going 300 miles is very small. If you produced it at 120 volts, then the amount of current you would have to send across California would be enormously large. And then you would lose most of it. And I think, actually you guys had a homework problem similar to this not too long ago. But this voltage here, if you did 120, you would lose something like 95% of your energy before it got to Santa Barbara. So if that's what you mean by lossy, yes. But
we could just as well have DC at 500,000 volts too, and then it wouldn't be lossy. So it's not so much that it's DC, it's that it's very easy to switch a low voltage AC to a high voltage AC, because all I have to do is generate it here and put a secondary that has thousands and thousands and thousands and thousands of turns. And I can produce something that starts off at 120 volts, and by putting it into a secondary, induce it up to 500,000 volts really easy. So it's not so much that the DC is lost as it is you want high voltage. And if you go back 120 years, there was no easy way to convert a low voltage DC to a high voltage DC. That was the big thing. And so the two competitors here, Tesla and Edison. Edison was doing DC, and his approach was, that's easy. You just put a power generating station in everybody's basement. And that's how electricity started. If you go back to New York City, all the, the Central Park, the Fifth Avenue there, all the rich people were getting away from the kerosene candles or lamps, and they had gone to electrical lighting. And to do that, they all had a generator installed in their basement. And so they say you could go down Fifth Avenue and it would all be lit up with electrical lightings, and people would do that because most people couldn't afford electrical lighting, and so the common people would walk down Fifth Avenue, except for no Rockefeller's house. What did Rockefeller sell? Kerosene oil. Yes, Rockefeller was concerned about going bankrupt, and he probably would have until the gasoline engine was developed. And so instead of making kerosene, he now made gasoline. And
wasn't gasoline a byproduct of making
oh yeah, and before the automobile engine, as you're making kerosene, a byproduct is gasoline. And it's like, what do you do with it? So they just let it go in the Hudson River, let it evaporate, all this gasoline. Got to get rid of this gasoline. It's really volatile. What are we going to do with it? And of course, the world changed here. Anyways, but it was Tesla who went with the AC, and Tesla's idea was far better. As you can see, it won out. Is not to put a generator in everybody's basement, or the switch was now to put it on every corner at every street block, but to make it AC and to put one giant one at Niagara Falls, run the wires across New York, and run the city off.
I think he said he could power the whole East Coast with one power plant.
He made some big claims. That was a little extreme. Yeah.
So how come we don't have 240 volts?
Well, so now there's a trade-off here, right? Because from an engineering perspective, the higher you make this voltage, the less losses you have. So from an engineering perspective, you're thinking, hey, higher voltage. But from a safety perspective, you're risking more fires, more people getting electrocuted, and so there's a trade-off. And the two I'm aware of, there could be others in the world. Well, okay, and I should actually rephrase that. So what we tend to do in residential areas is it's all at 120 volts. When you work in an industrial power plant, this is not 120. You've got numbers like 240, 440, and so you can make it at a lot more. Those higher voltage power lines don't usually go into the residential areas. They go into the industrial areas. And so you'll discover that as you start working in industry. You'll probably have a lab, and you'll look on your wall, and you'll have like 17 different plugs going. Let's see, that's 120, that's 240, that's 208 three-phase, that's 440 four-phase, and you'll go through the list and go, where does this plug into? And so they're all produced different for different patterns. So from the engineering perspective, higher voltage is better, but from a safety perspective, it's not. So all homes are produced this way, yeah. In the United States. Other places in the world, they went ahead and went higher in voltage
They don't have iron law.
They don't care about their citizens. No, I'm just kidding. But you know, it's certainly more efficient, but then you have the problem of the risk factor there. Yeah.
That DC voltage, it has a bunch of pumps on it, so would that typically a DC voltage, so switch it over that easily to...
Yeah, so as you're going to see in lab today, we are going to start off with that, and then we're going to switch it to that. All we've got to do is put a capacitor in here. And so while this goes here, we just charge up the capacitor. Then as the voltage from our generator goes down, we just use the voltage from our capacitor. And so just add a capacitor to those humps and you have a DC. It's, again, fairly simple design, and hopefully it'll make sense to you. Oh, let me show you another one here. This, again, just trying to do some more examples, hopefully getting across to you, it's kind of this same idea here. What about something like this? What if I just have a metal plate and a magnet? You probably saw earlier when I took this thing apart, here is a magnet. Here is a swinging metal plate. Now, to convince you that the bearings up here are pretty good, let me just swing it back and forth. Okay? Obviously, there's some loss there in the bearings and air friction, but it swings pretty good. Fair enough? What if I send it through the middle of a magnet? And I do have magnetic brakes. Or, in the case of an electrical car, I have a chance to take the rotation of the wheels, and when I apply the brake, regenerate that electricity and recharge the battery, so that when the light turns green, I can now use the electricity in the battery to make the car go again. And as I approach the red light, I then can regenerate that electricity, or I can apply the brakes and convert it into electricity and storing it in the battery. And so you will see a huge difference when the magnet is there and when it's not there. Why? Well, I think this picture does a pretty good job of it. They got a north pole towards us, which is kind of how I have it here. And so I will put the north pole out towards you. And so as this piece of metal goes into the magnetic field, isn't there a change in flux? If you look at this piece of metal, right now there's no flux. As it goes in, there is flux. In this case, the flux is going from north to south. And so the flux is increasing that way. So there should be a secondary effect. Which way should the flux be for the secondary? Pointing out. So I'm going to take my right hand, thumb out. Current should go around this way. We call these eddy currents, and that's what the author is trying to show here in the purple. He's got, look, what's going to happen is the current's going to be going this way. At least as it's going in, because what happens when it's swinging out? Yeah, remember, when it's coming out, which means it was already in, we already had flux going this way. And so as it is coming out, we are getting less flux. To make up for that less flux, the secondary is going to make flux in. I will take my right hand, point my thumb in, my fingers will curl this way. And so I will get a current in the opposite direction. So here is clockwise, here is counterclockwise. Now, if you look carefully at this, let's look at this secondary effect. If current is going around in this direction, in this loop, and maybe I should come over here, this loop with the current going around this way, if there's current in here, which side would you think of as the north pole of the magnet created here? So current goes around here. Oh, I'm sorry. I was doing my fingers wrong. That got to match it. Okay, right. So this way. So as I go around this way, which way would the field be? So I would say this side would be a north pole, and this side would be a south pole. But let's just focus on this side, north pole. This is a north pole, and that magnet is a north pole. What happens as two north poles come near each other? Yep, they repel.
as it starts to move out, and the current goes around this way, what would you call this side of the metal here? A south pole. And so as it is coming out, this would be a south pole. And what would you say about a south and a north? They would attract. And so this object is being blocked as it comes in and being pulled back as it tries to go out. And basically all the kinetic energy turns into electrical energy, which in this case just goes right to heat. And so we only generate heat. But if I were to hook this to a battery, I might be able to take that electrical energy and charge up my batteries. Yeah. Go ahead, Danny.
Wait, so would the effect be more effective for more electrically conductive things or less electrically conductive things because less current then?
Well, if I'm trying to get more current,
You want more electrically conductive.
yeah, then I would want more electrically conducting.
Would be more effective for electrically conductive things like copper.
Yep. And I just had pieces of aluminum, so that's what I'm working with here. But do you know anything different about this one? Yeah, I took the bandsaw and I cut notches in there. Does that change anything? What will it change? When this moves through and induces a voltage, it will still induce the same voltage. But will I get the same current? No, those little cuts are going to block the current. Now I must admit, maybe I didn't make them close enough, but there's always going to be a little bit of current inside there, but most of the current is being blocked. And so what do you notice? Different. Now, no braking effect. I'm not inducing any current. Isn't this fun? And it depends on you and your personality. Some people don't like physics at all. I can't imagine that. And some people like mechanics more than E&M. I have a hard time understanding that one too. But for you civil and mechanical engineers, great. We need mechanical engineers. We need bookkeepers. We need all kinds of other people. But this electromagnetic stuff is really, really fascinating, at least to me. And to me, kind of the funnest part of the class and this whole three sequence, except for maybe the thermodynamics, that's pretty cool too. But this stuff here is applied. Yeah.
If you had the original one and you lift the magnet, would it do the opposite, or would it just change the direction?
Well, the currents that are produced here would be opposite. But the poles of the magnet are also opposite. So this north pole is now on that side, the current goes the other way, which is the north side, so the effect of braking is still the same. So if I do it that way or turn it around, the mechanical part of it is the same. So, depending on what you're asking. If you're asking mechanical is the same, yes. If you're asking electrical, no. Yeah.
Does the magnet get weaker every time you do that?
No. There's no energy coming away from the magnet. The energy works this way. I give it potential energy. It turns into kinetic energy, which then turns into electrical energy, which then turns into heat. That magnet did nothing more than induce the current. It didn't take energy from it, didn't add to it, no energy there.
Could magnets also be used in damping oscillations?
Yes, and they are. This is a perfect way of damping, an oscillations. Again, our part of the world, we don't see subwaves, but this is a great way of reducing the motion of a subway car, because the amount of braking is directly proportional to how fast it is moving. Because again, the EMF is related to the change in the field. So when I have a subway car that is going really fast, and I apply the magnetic brake to it, there's a lot of braking. But then as the subway car slows down and is going very, very slow, there's very little braking. And so the braking is proportional to how quickly it's moving. I'll leave this up here for those of you guys who want to play with this in a little bit. But here, if you just take a metal plate in here and you just kind of pull it slowly, if it's slow enough, you don't even feel any effect. You go, there's nothing going on here. But move it quickly, and you can feel how much your hand has to pull back and forth on this thing to overcome that magnetic forces. All right, well, I was hoping to kind of say all that long before 10:45, but let's see what else we can do here in terms of problems out of the back of the book. I've done quite a few problems for you, so I feel good about that. But at the same time, I really haven't done any directly out of the back of the book, but they are exactly the same way. Let's try number 18. 18 is a good one to do because I think it illustrates almost all the pieces that we've done, plus number 18. Where's 18? 19? 19, 18, plus 18 does a toroid. And all these examples I've done so far, none of them have been a toroid. So let's do the toroid. And that was, actually now that I think about it, it's also the toroid's the one that wasn't on the test. I tried to, as you know, mix a bunch of things together to get you kind of think about everything at once, which, especially number 3, got real long. But I had some problems with the toroid and just decided that that was just too much. And that I know that we have plenty of opportunity to do a lot of things with toroids from here forward because we're just going to see these magnetic fields again and again and again. So here's the picture on number 18. And here's what it says. It says a toroid has a rectangular cross-section where A is equal to 2 centimeters and B equals 3 centimeters. And the inner radius is 4 centimeters. It consists of 500 turns of wire and carries a sinusoidal current where it is equal to I maximum sine omega t, where I maximum is 50 amps and the frequency is 60 hertz. The coil, a coil consisting of 20 turns of wire, is linked with the toroid as shown in the figure. Determine the EMF produced in the secondary coil. I'll call it the brown coil. I'll start conceptually here. Is there going to be an EMF? I agree, it's not moving. But doesn't the toroid produce a magnetic field? Okay, and so we need to go back and think about this toroid for a moment. I'll draw the little rectangular cross-section first, that picture there. And so we have that little rectangular cross-section which has an A and a B. And if I were to look at the magnetic field from there, and I'll put that right inside of my secondary, we should have a very strong magnetic field near the inner part and weaker as we get out. In fact, what we just learned here in chapter 30 was that this is the strength of the magnetic field inside the tunnel part of the toroid. The donut hole part, and outside there is no magnetic field. But inside the tunnel part, there is. And so there is a magnetic field. And that magnetic field depends on current. And what they said is that current in the toroid changes with time. It is a function of time. It equals to some maximum value, sine 2 pi 60 t. So there is our 60 hertz. So this might be plugged into the wall in some way. They even say that the maximum is 50 amps. So this is quite a significant amount of current in that toroid. But it's that picture right there that hopefully will give you a clue that, does the magnetic field change then with time? Yes. And part of flux is the magnetic field strength, and therefore there's going to be a change in flux. And if there's a change in flux, then there is going to be an induced EMF. Now in this case we don't have to worry too much about direction, because the truth is the flux is going to go in and then out, and then in and then out. And therefore the current in the secondary is going to go counterclockwise, clockwise, counterclockwise, clockwise. And so we're going to get an alternating current in there. So again, not worrying about pluses or minuses, and not even worrying about direction this time, because we know we can't say the direction of the current is. We just know it does change. And so it goes one direction and then another one. So the problem says find the EMF. Well, that would be, and I'll just do magnitude, the number of turns in the secondary times the derivative of the flux that goes through our secondary. Okay, so we've got an integral, we got a derivative, which you probably begin to notice. But this might have been the first time we've ever had derivatives and integrals in the same problem. But remember, or watch, it's an integral over space, but it's a derivative with respect to time. So those don't undo each other. All right, so looking at this number here is the number of turns in the secondary. And so this number here would be a 20. Then I have to take the integral of the flux. And what makes this a little bit harder problem is that the magnetic field changes with position. But at least I know the equation of how it changes. So it's mu naught times n, and I'll put a sub p for primary. The magnetic field here is coming from the toroid. And then I will put current, and then I will put 2 pi r, and then I will put dA. And maybe the first thing to do is kind of scan through, and I'm going to do an integral over the area. Anything a constant in this equation? Okay, mu naught, number of turns in the primary. Anything else?
2 pi.
2 pi. Anything else? Is the current?
Nope, it's changing.
So the current does not change with area, but it does change with time. So I can pull the current out of the integral of space, but not past the derivative of time. Oh, and I forgot my cosine theta, thank you.
Oh, he's saying the R.
Oh, and I forgot my r, yes, that's more important. But this will be either 0 or 180 degrees, and that's why I blew that one off. Right, right. But the r is crucial, right? That one changes. And so kind of looking at this, just to point out then, I've got my 20 here, and these numbers here are a constant, not only in space, but in time, so I can pull them out. This one here changes with time, so I got to take its derivative. This one does not change with time, so I can pull it back or forward. It doesn't need to be part of my derivative of time. This one is a constant with time, and so those can be treated separately. And so as I begin to put in my numbers, I've got again the 20 from the secondary. I've got the 4 pi times 10 to the minus 7 for mu naught, which cancels with the 2 pi down below. I got the number of turns in the primary, and that's coming from the toroid. So there's the 500. Then I've got the derivative of the current. Well, that's what this is. So taking the derivative of the current, I would get the 50 amps. The sine would become a cosine, but the chain rule is going to get the 2 pi 60 here, that magical 377 we're going to see a lot. And so there's the derivative of the current. The other part of this is I've got an integral of the area. Well, again, that's why I think your author has said, where is the flux? The flux is actually only in this part, the tunnel part of the toroid. We don't really need to know or care about how big is the secondary, because the total flux comes only from what is in the primary. And so we want to know the flux in here. And I'm going to then chop this into strips. I better not write on the screen, but if I come over here and say, let's make this into strips and add up my strips, then this becomes the height A times the thickness dr, where here is one strip and it's going to have a thickness of dr and a height of A. And so now I can add them up. And in this case, it looks like we would start with an inner radius
For that,
of capital R. And
that integral of the A is constant, right?
Yeah. And so as you are noting, I can pull the A out. And so what I have is my 20, my 2 times 10 to the minus 7, my 500 for the number of turns in the primary, my 50 for the maximum amp, my angular frequency, the 377. The A, well, since we're about out of time, I'll just put A, but they think they said 3 or 4 centimeters, something like that. I'll look at that number in just a second. But then I have a natural log of R plus B over R. And so there would be the EMF produced for that one. It wasn't that simple. All right, well, good luck. Highly encourage you to go to MC for these and CDON. Maybe start seeing them about 8 in the morning and all the way till 6 at night and so forth and so on.